Hey, welcome back. We are continuing Chapter 6 in this video. We've already introduced some of the truth tables for the sentential connectives. In particular, we looked at and, or, and not. And or are binary connectives. Their role is always to join together two chunks, two other things. Often, that's going to be two atomic sentences. Sometimes it might be something more complex. It could be two other complex sentences, such as P and Q and R. What's important here is that we always remember to use brackets to disambiguate what we mean, so that if we have a complex statement with many sentential connectives, there's always a clear main logical operator, something that separates the overall sentence into binary chunks. We also talked about the negation. Now, the negation is not a binary operator. It operates on the next thing in line. So if I have not P, it's operating on the P. If I have not and not brackets P and Q, it's operating on the and. So hopefully the last couple of videos have made that more or less clear in your mind. Otherwise, watch them again, work a little bit on SL, do some of the practice exercises in the book, and it'll come to you. Now we should be moving on and talking a little bit about the next truth table, which is the conditional. This one's a little bit more tricky. The truth table of the conditional, you can see it right here, has falsity in only one circumstance, when P is true but Q is false. Now P and Q, again, could be atomic sentences, or if you're connecting something more complex, it could be a longer sentence. But it will always work the same. The input here is two things, the right-hand side, the left-hand side, and it's going to be true, true, true. So when both sides are true, the if itself is true. But it's false under one circumstance, when true, false, false. Now it's supposed to capture our intuitive notion of consequence, of if this, then that. And it's only going to be falsified in one case, when the antecedent, the thing causing, is present, but the consequent, the effect, is absent. And it's going to be true otherwise. Now, this might seem strange, and every time I teach this class, I have no shortage of students telling me, why is this the only case where it's false? Why is it true when the antecedent is false? Well, there's a couple of reasons for this. One thing you should think about is the fact that there's only two truth values. So we don't have indeterminate as a value. So if I say, if I go to my friend's house, I'll play video games, and I don't end up going to my friend's house, why would that conditional still be true? Why wouldn't it be indeterminate, because you don't know what would have happened? Well, because it wasn't falsified. And roughly speaking, what we're really interested for us is the falsification conditions of a statement in this case. So you can accept my reasoning here, or just kind of accept the truth table as the way it is. We only have two values. It's either going to be true or false. If the antecedent is false, we haven't actually showed the conditional to be false, so we might as well just have it as true. Because we don't have the value indeterminate. So let's look at the truth table again. So what we have is true, 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 false, 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 true, true, false, false, true. Again, right, we have one case where it's clearly falsified, and if we want to say something different, if we want to have a sentence where an antecedent's falsity makes the sentence false, we can express that in sentential logic. That's kind of the nice thing about sentential logic. We saw it in the inclusive versus exclusive or. If you have an inclusive or, but you want to express an exclusive or, you just need to add a little bit of complexity to the sentence. You say one or the other, and it is not the case that both. That's something we did in the previous video. So for now, this truth table, because again, there's only so many truth tables you could have, because there's only two truth values, is the one that is used to express the conditional statement. And it works actually quite well. So it's only falsified in one case, where P is true, but Q is false, which is, again, kind of what you expect, right? If I say, if you water the plants, then they'll grow, and then I water the plant, then you water the plants and they don't grow, then I said something false. However, if you don't water the plants and they grow anyway, I didn't say something false. I said, look, if you water the plants, they'll grow. The result of watering the plants is growth. And it's only falsified, it's only shown to be false if you do the thing and then the effect doesn't happen. Right, so Under what conditions is the sentence falsified is the way you should think about the conditional. All right, when am I lying? If I say, look, if I go to my friend's house, we're going to play video games. If I didn't go to my friend's house, I didn't lie. I said, if I did, that's what we would do. And there's no indeterminate value. So we're going to consider that true. It's only false if I go to my friend's house and then I end up, setting fire to things, which is a hobby I used to have as a kid. If I go to my friend's house, Mom, I'm just going to play video games. And then I go and I ended up committing arson. Well, then I get in trouble. But if I don't go, I didn't lie, and I can't be in trouble. So it's only false. It's explicitly false in only one case. So let's think about these other examples too, right? If the car gets a scratch, you'll get in trouble. When is that false? I get a scratch and I don't get in trouble. If I study, I'll get a passing grade. I study, I don't get a passing grade, then the statement's false. So the conditional, has this particular truth table where it's only false in one case, where the antecedent is true, the consequent is false. Again, I want to really repeat that the important thing is not having this conceptual understanding of the sentential connectives in your head. As I said in the first video, this is a skill. It requires practice. You should be looking in the book and doing all the exercises you can find. In particular, you should be memorizing these truth tables. You shouldn't be trying to understand the idea of if-then in your head. What you should be able to do is close your eyes and write all the truth tables by heart without looking it up. Just be able to go like P then Q, right? True, false, true, true. Just memorize them. Know them like the back of your hand. Rewrite them and rewrite them until you don't make any mistakes. Once you know the truth tables by heart, your success in sentential logic will be assured. So the point of the conditional is to memorize the truth table. But it's also to assert that if some condition is met, some further thing will also be true. So it's false when the conditional is met, but the consequent false, because that's the point of it. It's going to assert that the consequence of something, will happen, that there's an effect. What it does not assert is that the consequence could not happen some other way, which is something we kind of talked about in another video when I was being a bit more informal about our logic. Suppose I say, if I win the 649 lotto jackpot, I'll be rich. Then I become rich by investing money in the stock market or in Bitcoin 10 years ago. Well, the sentence isn't false thereby. And let's kind of look at the truth table to see how this works. Because we've been doing things a little bit informally. But the truth table kind of brings out how this informal reasoning can actually be demonstrated. So here I say, if I win the lottery, then I will be rich. And if I do the truth table, true, true, false, false, true, false. Now, why am I doing it this way? The reason is pretty simple. Because this exhausts all the possibilities of combinations. True, 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 false, false, true, false, false. There's no other combination. That's all combinations of T and F that are possible. And then I define the value of the and here, the if-then, as follows, which covers every possible case. So the if-then is fully defined with the truth table because, given the parameters of our logic, that things can only be either true or false, and that this is a binary connective, there's no case that isn't covered by the truth table. True, false, true, true. Now, suppose that, if I'm saying, hey man, if I win the lotto, I'll be rich. Then it turns out that I invest my money, I do really well, and I end up rich. So it's false that I won the lotto, but true that I'm rich. Is it still true that if I won the lotto, I'd be rich? Yeah, it's still true. If I had won the lotto, I would have been rich. So this is still true. If I win the lotto, then I'll be rich. I don't win the lotto, I'm not rich. Is it still true that if I'd won the lotto, I'd be rich? Yeah, so still true. I buy a ticket, I win, I'm rich, still true. So there's only one case here left where it's obviously false. I win the Lotto 649 jackpot and it turns out I'm not rich. How would that happen? Suppose I didn't think about what to do with the winnings and I lost it all to taxation and a messy divorce or something. then all the money's gone, and I won the lotto, but I'm not rich. Or I won the lotto jackpot, but as I cash in the ticket, it's stolen from me. So I won, but I can't receive the winnings for some reason, right? So it's true that I won the lotto, but it's false that I'm rich. Then I said, hey, if I win the lotto, I'll be rich. But that's the case in which it's falsified. All the other cases are true. So if you think about the falsification conditions for the conditional, it actually quite makes sense that we have the truth table we have. Also, you have to think that there's only so many of these truth tables that are actually possible. How many combinations of T's and F's are there for binary connectives? There's, what, 16 possible truth tables? If we're going to translate and, or, if into the limited power, into the limited expressive power of SL, you're going to have to make a decision. And this truth table actually does a surprisingly good job of capturing what we mean by if-then. Here's another subtlety. Suppose I want to say that the only way I could ever get rich is if I won the lottery. Well, I can't say if W then R. But here's the interesting bit. If I reverse the order, that actually does the trick. If I win the lottery, I'll be rich. Okay, that's if W then R. So I'm saying it's a consequence of winning the lotto that I'll be rich. But suppose I want to say only if I win the lottery, I'll be rich. That's the only case it's possible. Then you just reverse the order. Because it's saying, effectively, if I am rich, it's because I've won the lottery. It's the only way it's possible. So if you observe me being rich, then you can deduce that I must have won the lottery. Right? If winning the lottery is the only way I could get rich, only if I win the lottery will I ever be rich. Don't go to grad school, kids. Then it's true that I'm in fact rich. It must be the case that I won the lottery, which is exactly what the truth table will say. Because suppose I actually reverse these. Let me, I'll shift W here. All right. Suppose I say, is there room? All right. Suppose if I say if R, then W. You know, I probably put this on a slide. I bet you if I just go one slide ahead, I don't actually need to write it. Yeah, there it is. Right. This is the if versus only if truth table. But why don't I write it out anyway, because I think it's more natural if I do things on the board, I guess. So we're just going to keep the T and F the way it was before. Right, so true, true, false, false, true, 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 false, true, 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 false, 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 true. Right, so here we have, I'll only be rich if I win the lottery. If rich, then it's because I won the lottery. When is that statement false? I am rich, I didn't win the lottery, therefore my only statement is falsified exactly where you want it to be falsified. So if I say, the consequence of winning the lottery is me being rich. If I win the lottery, I'll be rich. If I say, only if I win the lottery, I'll be rich, I want to reverse the order of the conditional. That's actually a really neat feature. It's one of the reasons this truth table is such a genius. If I say, if I'm rich, then you can infer that I must have won the lottery because I said the only condition under which I'll ever be rich is if I win the bloody lottery. It's the only way because I went to philosophy for my PhD. What am I doing with my life? Okay, so by reversing the order, we capture the idea that there's one way of, right, the only if is kind of captured there. I thought that was pretty interesting. Okay, Alt Shift W. Okay, next slide. So here's another example to just kind of understand the conditional here, the if versus only if. If I say only call if there's an emergency, then I'm saying something like, if I'm calling, then you can infer that there must be an emergency. Versus, if there's an emergency, call. If emergency, then call. Notice that sentence 1 is false if there's a call but no emergency, because it specifies that the only time you should call is if there's an emergency. So, however, if I say, if there's an emergency, just call, I can call anyway. You didn't say only call if there's an emergency. I could call for some other reason. You're just, in sentence 2, you're telling me what to do in the event of an emergency, which is that I should call. But if I say only call if there's an emergency and I hear my phone ring, I'm like, oh, something must be going down. So the truth tables here are going to be different because the falsification conditions, which we just looked at, are going to be different. A conditional, remember, is false when the antecedent is true. The antecedent is true, but the consequent is false. If makes a statement about the consequence of a thing occurring. Right? The consequence of something occurring is an if statement. If something, the downstream result is that other thing. However, if I say only if, I'm making an assertion about the conditions required for something to happen. Only call if there's an emergency. Why would I say that? I'm saying a condition required for calling to happen is an emergency. So if I'm calling, you know there's an emergency. That's what I can deduce from it. So I would say, right, if calling, then there's an emergency, as opposed to if emergency, then call, because I could call for another reason. Okay, let's move on to the next slide about if and only if. How many slides on if and only if do I have? Okay, so just the way to think about the conditional, and it's a tricky one, is that when we say if P then Q, we're saying something about P. We're saying that the outcome of P's being true is that Q will also be true. And we're not saying anything else. Right? We're saying something about the antecedent. We're saying something about P. We're not saying anything else about what could make Q true. So the consequent could be true a bunch of different ways. Right? Being rich could occur in a number of different ways. I could start a successful business. I could invent a time machine and buy Bitcoin in 2008 like I thought I should when I first heard about blockchain technology. Oy vey. So there's a bunch of ways of being rich. So if I say if I say like if I win the lottery I'll be rich, I'm saying a consequence of winning the lottery is being rich. But I'm not saying that's the only way. But only if I say only if P then Q, then I'm saying something about Q. I'm saying only if P then Q. I'm saying the only condition where Q is true is the one where P is true. Right? So if I say only if I have the flu, I'll stay home. The consequence of me having the flu is that I stay home. Right? So if I have the flu, I'll stay home. If I have the flu, the consequence is that I'll stay home. Only if I have the flu will I stay home. The only situation possible in which I stay home is if I have the flu. So if I call my boss, I say, if I have the flu, I'm going to stay home. But I could stay home for another reason. It's perfectly compatible with that. Often, in natural language, when we make if statements, we're meaning only if statements, right? So if my boss calls me up, he's like, are you coming to work? Well, if I have the flu, I'm going to stay home. I'm basically implicitly saying that I will be coming in unless I have the flu. Only if I have the flu will I come home. I'm implicitly saying that. But in logic, we're going to want to keep these two ifs actually really, really distinct, right? An if statement is saying something about the antecedent. An only if statement is saying something about the consequent. That's pretty catchy, right? All right, if versus only if. Here are the truth tables. Again, I just wrote them, right? But you can see that they're quite different. Okay. Again, you should have these truth tables at the tips of your fingers. You should be able to just write them out all the time, first time. Just memorize them. I was looking at the clock. Okay, so here's a good practice exercise to see if you've really kind of mastered the subtleties of the conditional and sentential logic. Unless is another way of expressing a condition. If I could say, for example, this plant will die unless it's watered. So what you should do is pause the video and explain in your own words what condition is being expressed in sentence 1. Then replace unless with an if then. And here's my hint. You should use a negation somewhere in that. All right. So this plant will die unless it is watered. Try that out. Pause the video. Oops. This plant will die unless it's watered. Did you pause? All right. Let's talk about the solution a little bit. Plant will die unless watered. P unless Q. What we're saying with the unless is that something will be the case unless something else prevents it. This plant will die unless it's watered. So this plant will die unless it's watered. Plant will die will occur unless something prevents it. So basically what I'm saying is that the plant will die is the consequence of something. What is it the consequence of? It's the consequence of it not being watered. So another way, just think about the conditional in terms of what makes a statement false, because the falsification condition is the unique case. That's the one you want to find, and you want to build the rest of it around that. You want to build your conditional around its falsification. One would be false if the plant is not watered and doesn't die. So if somebody says, like, that plant is going to die if you don't water it, when would that person be wrong? When would that person be incorrect or lying? Well, the person is wrong. This plant will die unless it's watered. When are they wrong? If I don't water it and it lives. When watered is false and die is false, or when not watered is true and die is false. So one is saying that if the plant is not watered, it will die. It's saying if not W, if not watered, then D. And why is this so important? Think about the falsification conditions. Okay, turns out I don't have, so if not W, then D. Let's do that one on the board. All right, so the plant will die unless it's watered. So plant will die unless it is watered. This is a conditional. What kind of conditional is it? It's saying that the plant will die as a consequence of something. Unless it's watered, the consequence of it is that it's going to die. So one way of saying is that if not watered, then it will die. The consequence of it not being watered is it's dying. Now, the way I told you to think about it is in terms of the falsification conditions, i.e., when is somebody saying something that is not true? Now, when is a conditional false? When the antecedent is true, but the consequent false. So die is false, but not watered is true. So watered is false. And that is the actual falsification case I'm interested in. It is true that I don't water it, and it is false that it died. Now, I didn't water it, and it's just fine. So what you said is not true. Therefore, if not water, then die is the right way of doing it, because it captures the case in which this statement is shown to be false. Right? The case where it's true that it's not watered and it's false that it dies. Right there, you might want to think about other ways of representing that statement to see if it works. The plant will die unless it is watered. So if I say, if it died, then it wasn't watered. Is this a good way of capturing the unless? If it died, then it wasn't watered. Well, no, because it could die for all kinds of reasons. So again, the plant will die unless it's watered. I'm basically saying that if you do not water it, it will die. So suppose not water is true and die is false. So false, true, true, right? Because on the conditionals truth table, if the antecedent is false, the conditional itself is true. So here I'm saying, well, I didn't water it, and it didn't die. So true. But that's not right, because in this case, this statement, the if then comes out true on the condition that I should intuitively say that it should be false. You said the plant will die if it's not watered, right? If not watered, then die, right? And then I didn't water it, then it didn't die, false. However, on this one, the statement is, if this was the translation, the statement will come out true on what should be its falsification conditions. So it can't be the right translation because it doesn't capture the falsification conditions adequately. Again, slowly. How do I want to translate this? I want to translate it using a conditional that captures when the statement is false. When is the statement false? It is false when I don't water it and it doesn't die. And that equals, right, false. So how do I get that? If not water, then die gets it. If die, then because it's not watered, right? However, if I flip it like that, I'd say the only way this plant would die is if it's not watered. It's an only if, but that's different. Okay. Okay, here's some interesting logical equivalencies, and we're going to stop here because we're about 24 minutes deep into the video, and we have some more stuff to do. So logical equivalency, if you remember a couple of videos ago, has to do with the idea that the sentences mean the same thing. In other words, that if one sentence is true, its logical equivalent will be true, or if it's false, its logical equivalent will be false. They're expressing the same thing. Now, there are different interesting logical equivalencies. There are logical equivalencies, for example, between neither P nor Q and not P and not Q. Let's look at that one very briefly, actually, before we look at the truth tables of the examples I have. So, by the way, I'm proceeding this way before I give you like a full recursive definition of the syntax of sentential logic, because I want you to be familiar with how to construct sentences and look at truth tables and kind of know the truth tables, because then when we jump into the syntax, you'll have the kind of the basic practice of it, because I really do think it's a practice-based thing. So again, pause the video, do the exercises, look at the book, look at Chapter 6, which is what we're doing right now, and do all the exercises you can find. All right. So here's an interesting logical equivalency. Right? If I say neither P nor Q, not P and not Q. All right. So speaking of pausing the video, why don't you grab a scrap of paper, pause this video right now, and prove that they're logically equivalent. How? By writing the truth table for both. Write the truth table for both and see that underneath the main logical operator, you have the exact same values. Go. Pause video. Okay. So the main logical operator, of course, is the one that connects to everything else. Under a binary scenario, it's the one that connects the other chunks, as it were. So the main logical operator, MLO for here, is the AND. However, for here, it's the negation, MLO, main logical operator. So let's complete the truth table here. Which one should we do first? Why don't we do the neither P nor Q? It is not the case that what? Either P or Q. So the brackets mean that where is the value of the negation coming from? It's coming from the value of the OR. Where is the value of the OR coming from? From the P or Q. So where do we start when we build a truth table? Well, we start with the lowest level components and build up towards the main logical operator. So let's do that. Let's build up towards the main logical operator. So we have two sentence letters, two variables, and therefore the possibilities are going to be true, true, false, false, true, false, true, false. Eventually, we're going to deal with sentences with more than two sentence letters. We're going to have P, Q, R, S, and I'll show you how to do the truth tables for those. For now, the important thing is by going true, 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 false, false, true, false, false, you'll be exhausting all the possibilities when you have two sentence letters. Notice probably the easier way to remember is like true, true, false, false, and then you go true, false, true, false. So let's look at the answers here. So P or Q. What's the truth table for regular disjunction? P or Q. True, 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 false, true, false, true, true, false, false, false. Because the value of the disjunction is a function of the value of its inputs. The truth table we've defined already says that this is just this regular disjunction truth table, true, 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 false, false, true, false, false, false. So then we flip the values, because this disjunction is going to be the input of the negation. True gets flipped to false, true gets flipped to false, true gets flipped to false, false gets flipped to true. False, 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 true under the main logical operator. Good. What about this one over here? The main logical operator is here, so we have to again work from the most basic parts, which are going to be the sentence letters. We're going to do the same thing. True, true, false, false. True, false, true, false. This is important that we keep consistency across our two statements when checking for equivalence. Now, what's the next step? Well, the main logical operator is the AND. Where is this going to take its values from? From P and Q? No, for their negations. So now we have to do this complicated thing where we flip the values. True, false, true, false, false, true, false, true. Likewise over here. True, false, true becomes false, false becomes true, true becomes false, false becomes true. And these ones are going to be the values that feed into the AND. All right, so let's see what it looks like. False, 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 because it's an AND. Right? The AND is only true when both of its sides are true. False, true, false. True, false, false, because both need to be true. True, true, true. So what's the value of the main logical operator here? False, 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 true. False, 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 true. So these two are logically equivalent. The idea here, of course, is that they mean the same thing. And you think about it semantically rather than through the truth tables, you kind of see why. Neither P nor Q is the case. It is not the case that either P or Q. That means the same thing as not P and not Q, right? I neither liked the Phantom Menace nor Attack of the Clones. I didn't like the Phantom Menace, and it's not the case that I like the Attack of the Clones. Prequels. Prequels are bad movies. All right, so let's look at some other logical equivalencies now that we understand the basic idea. Alt-Shift-W. Here's some other ones. The truth table for the conditional is actually really interesting, because you see that the middle one here's the conditional. It's equivalent to not P or Q, where the main logical operator is bolded here. Either not P or Q. It's also equivalent to if not Q, then not P. So these are kind of really interesting logical equivalencies here. We'll see that the truth tables for if P then Q are actually equivalent to slightly different sentences, which means that they express the same thing. The conditional is equivalent to a specific disjunction where the antecedent is negated. So that's actually a really interesting little equivalence there. And you can see that it's true if you just kind of work out the truth table, which is something that might be worth doing, right? We have true, true, false, false. It's flipped by the negation. The negation feeds into the or. False, true, true. False, false, false. True, true, true. True, false, true. So it's really interesting, which kind of makes sense. If you think of the conditional as saying, if P is true, then Q will also be true. So it's saying, well, so the disjunction is saying, well, look, two things could happen, or both of them. Either not P is true, either P is in the case, or Q will be the case. And that actually works out to be the same thing. So it's either not P, or it's going to be Q, or both. So if it's not P, or if it's not P, so if not P is the case, then what's going to happen? Then, right, if false, false, then true, true, or it's going to be Q. Q is true, 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 right? So it's actually kind of an interesting little equivalency here. So the next thing we should be working on is one more truth table for the biconditional. I'm actually going to stop right here. And thanks for watching. Next video, the biconditional. All right, thanks for watching. And again, work through those practice exercises in the book, as many as you can. And don't be afraid to, rewatch any sections you need to rewatch. Thanks a lot.